Numerical Methods Problem 13.7. Consider the following function. f of x is equal to negative x to the fourth minus 2x minus 8x squared minus 5x. Use analytical and graphical methods to show the function has a maximum for some value of x in the ranges of negative 2 to 1. So, here's our equation given to us by the problem. We're going to have a range of negative 5 to 5 for our graph. And since our maximum should be in between the points of negative 2 and 1, our lower bound check will be negative 2 and our upper guess will be 1. Then we need to compute the golden ratio, since we're going to use the golden ratio search to find the maximum in this problem. And then we multiply the golden ratio by our upper minus our lower. And then we compute our x1 and x2 values for the golden ratio search. So we add our d value that we found here to our lower to find x1 and subtract our d value found here from x upper to find our x2. Down here we plot up our separate values of x1, x2, x upper, and our x lower in different colors for our first figure. And then for our second figure, we'll show the actual approximation after our golden ratio search has been used and gone for 20 iterations. So we use our golden ratio search and then update it by the conditions of the golden ratio search. So if x2 ends up being greater than x1, then x upper is equal to x1, and if x1 is equal to x2, x lower will stay the same, and then we must compute d again to find our next x2 value. Otherwise, if f of x1 is greater than f of x2, then x lower is equal to x2, x2 is equal to x1, our x upper will stay the same, and then we compute our new x1, and we'll loop through this until we get our maximum value. So let's run it up. As you can see in the first figure, figure 1, we have our values that we plotted in our different colors. We have x1 in black, x2 in pink, and our lower in red and our upper in green. And so, just like said before, if our x2 in black is greater than our x1 in pink, then we will replace our x upper here in green with x1, which is here in black. And conversely, if f of x1 is greater than f of x2, we take our x2, which is here in pink, and make that our new x lower, so the red would go to the pink. And essentially that's what happens. And after 20 iterations, here I just have the graph showing the upper and lower values. We approximate our maximum value. And as you can see here, both our lower and our upper points are the same, and the same with our maximum value. At negative 0.4192, we have a maximum value of 1.4977, and we can always check this. Let's go to Wolfram Alpha. We typed in our same equation here. We got the same plot here. And then down below, we get our maximum at 1.497 at the x equals to negative 0.419, which matches the results that we found using the golden ration search in MATLAB. And that is all for problem 13.7.